Moments of inertia for area, also known as the second moment of the area. Here are our learning outcomes for today's lesson. Define moment of inertia, calculate polar moment of inertia, and interpret physical significance. So what is the moment of inertia? The moment of inertia for an area, also known as the second moment of area, is a geometric property that measures how the area of a cross-section is distributed around a specific axis. This is important because it tells us how much a beam resists bending when a force is applied to the axis. This is a fundamental concept to understand because in engineering, the moment of inertia is crucial because it directly affects how much a beam bends under a load. Beams with higher moment of inertia will bend less, making them better for supporting heavy loads. This is why selecting the right cross-section is key in beam and column designs. To understand this concept better, let's look at a visual representation of the effect of cross-sectional geometry on bending, moments of inertia. In structural engineering, the moment of inertia plays a crucial role in determining how much a beam bends under a given load. Even if three beams are made of the same material, their resistance to bending can vary significantly depending on their cross-sectional shape. So let's consider three beams of the same material, length, and applied force, but with different cross-sections. So first we have the thin rectangular beam, which bends significantly because its moment of inertia is low. Next, we have the I-beam. This shape has a much more higher moment of inertia, making it much more resistant to bending. Lastly, we have the hollow rectangular tube. This shape is also very efficient, reducing weight while maintaining high resistance to bending. So, to look into the beam setup, we have each of the beams which is simply supported at both ends. A central downward force is applied at the middle of each beam, and the material remains the same for all beams. When looking at the bending behavior and deflection comparison, the thin rectangular beam has a small amount of inertia, because most of its material is concentrated near the neutral axis. When a load is applied, it bends significantly because it does not have enough resistance to bending. It is not an efficient shape for structural application where bending resistance is needed. Next, the I-beam has fangs on the top and bottom with a thin web in the middle. The material is distributed far from the neutral axis, increasing its moment of inertia. It bends much less than the rectangular beam under the same load, making it more efficient for structural applications like bridges and building frames. Lastly, the hollow rectangular tube has an even more higher moment of inertia than the I-beam because the material is distributed around a large area. The hollow section reduces weight while maintaining strength, making it useful in lightweight structures. It bends the least among the three beams under the same load. Mathematical definition. Consider figure A in the given diagram, which lies in the x and y plane. The formula to calculate this is given by the moment of inertia is equal to the definite integral of y squared times dA, where I is the moment of inertia, y is the perpendicular distance from the axis to an area element, and dA is the small area element. The r value in this diagram represents the shortest distance from the origin to dA. The polar moment of inertia is given about the z-axis. So that is equal to JO is equal to the definite integral of r squared times dA, which is equal to the moment of inertia in the x direction plus the moment of inertia in the y direction. Note that since we square the distance y, the units of the moment of inertia are always in length to the fourth power. So meters to the power of 4, inches to the power of 4, etc. Now to understand the first and second moment of area. So the first moment of area relates to the centroid and distribution. So the first moment of area measures how the area is distributed relative to an axis. It helps determine the centroid, the center of mass, of a cross-section. This is defined as the definite integral is equal to y times dA, where y is equal to the distance from the axis to the differential area element dA. An analogy to think of this is similar to the moment of force, so torque is equal to force times distance. The first moment of area is area times distance. So the first moment of area is used in shear stress calculations and to locate centroid of a shape. So the second moment of area mostly relates to the resistance to a bending. The second moment of area is also known as the moment of inertia for area, measures a shape's resistance to bending. It considers how far the area is distributed from the axis. This is defined as the moment of inertia is equal to the definite integral of y squared times dA, where y squared is equal to the squared distance from the axis to the area element. An analogy to think of this is like the moment of force. Again, torque is equal to force times distance. The second moment of area is now squared, so it's area times distance squared. So the second moment of area is used in beam bending and deflection analysis to determine structural strength. Now let's get into our example problem for today. So in our problem, we're asked to determine the moment of inertia of the shaded area shown in the figure about the x-axis. Feel free to pause the video and try this problem on your own. When we're looking at our diagram, we can see that a differential element that is parallel to the x-axis is the rectangular figure that is shown in the blue curve, and that is what we're going to use for integration. So it intersects the curve at the arbitrary point xy. Since this element has a thickness of dy and intersects the curve at the arbitrary point, its area is dA is equal to 100 minus x dy. Furthermore, the element lies at the same distance y from the x-axis. Hence, integrating with respect to y from y is equal to 0 to y is equal to 200 millimeters, we have the moment of inertia is equal to the definite integral of y squared times dA, which is equal to y squared times 100 minus x times dy. And our final answer should be 107 times 10 to the power of 6 millimeters to the power of 4. Now let's look at some standard formulas for some common shapes about the neutral axis, starting with the rectangle. So we have the rectangular area, which the area is equal to the base times height. And we have a dot in the middle, which represents its centroid. The area of moment of inertia for a rectangular area can be found using the moment of inertia is equal to 1/12 times b times h to the power of 3. Next, for a triangular area, which is equal to 1/2 times b times h, we can find the area of the moment of inertia by 1/36 times b times h to the power of 3. Finally, when looking at a circular area, which is pi times r squared, we can find the area of the moment of inertia by calculating 1/4 times pi times r to the power of 4. In summary, we found that the moment of inertia about the x-axis is 107 times 10 to the power of 6 millimeters to the power of 4. And we also learned the difference between the first moment of area, which measures area distribution relative to an axis, and the second moment of area, which measures resistance to bending.